Okay, so existing work on this trade-off between existential risk and growth has all assumed that stagnation is perfectly safe. We saw two examples of that this morning from Chad and Tom. In both cases, if we just didn't develop any AI or whatever, the chance of a catastrophe was zero. You might wonder what changes if it's not. What if new tech can mitigate existing risks in addition to creating new ones? This will be somewhat analogous to the point that Chad raised about medical innovations lowering like the average person's annual mortality risk, but we'll be thinking about it sort of in a dynamic sense, where it's not just AI kind of temporarily can create some new risks and lower some old risks, but that over time continually risks can be introduced and mitigated. So we'll start with this really simple model in which the only kind of risk is state risk. And what I mean by that is you've got a hazard rate, a probability per unit time of an existential catastrophe, not an exogenous one, but one driven by the state of technology. So concretely, we'll say that the hazard rate is just some arbitrary function of the technology state, okay, delta of A. And it's non-negative. You can't have like a negative chance of dying. And we'll say that it's continuous, but it can be increasing or decreasing. So if the tech developed just after a given like technological frontier A on balance raises risk, then delta of A plus T plus epsilon is going to be higher than the delta you started at. But it could also be lower. Does that make sense? A is just baking in every risk relevant feature of the technology state. So, for instance, between T and T plus epsilon, we could develop easier ways to create devastating viruses that could kill everyone, or ways to make vaccines more quickly, which would like lower the chance that someone releases something that kills everyone per year. Okay. S sub T will denote the probability of survival until T from the beginning, which is time 0. It turns out that that's just equal to e to the negative area under the hazard curve from now to T. And I have an endnote working through why that is if you're not kind of familiar with thinking about hazard curves. The point is, this is what you get when you say, okay, we start out with S0 equaling 1, because the probability we make it to time 0 is 1. Obviously, we're alive now at time 0. And then the decay rate of like chance that we've made it to some time is it's just like the negative of the hazard rate times like the probability we made it to that time to begin with. And then you kind of integrate, you divide by S, you get something that you can integrate over time, and that's the formula you get for probability of survival to big T. Okay. All right. So that hazard curve, that's the curve of probability of dying per unit time over time. And the area under the hazard curve for all time, I'll call cumulative risk. That'll be big X. So the probability of surviving forever is e to the negative big X. That's S infinity. It probably doesn't mean survival like literally forever, but just survival to some like the T upper bar from yesterday when we were thinking about exogenous risk, but it could be like the end of the universe or something in a trillion years. So S infinity is the probability that we never succumb to a technological existential catastrophe and get to sort of make it through the time of perils or whatever and enjoy a long future. That's e to the negative X. So as you can see, survival is possible if the area under the hazard curve is finite, because e to the negative of a finite number is positive. And it's impossible if X is infinite. We don't need to actually reach a perfectly safe world necessarily and stay there. But if year on year things get safer asymptotically and they get safer fast enough, we could have like a positive probability of never blowing up. Any questions on that? Yeah. So far, yes. Later, when we think about policy and trading off between consumption and risk, A will index something relevant to both risk and consumption, and we'll have like another variable as well, but we haven't gotten there. Here, the only interesting thing about A is how much risk it comes with. Does that make sense? But I mean, does this should be sensible and self-contained with. Yep. It
seems like what you're saying is
yeah, but so there can be like a big space of possible technologies, and there is some path through that space that in fact we will traverse. You know, like maybe we could change it, but if we change it, then that change thing will be the path we traverse. And so this is just saying, this is just like marking out a particular, like path through the state space. I mean, honestly, A doesn't have to be a scalar here even, right? A could be a vector, A could be whatever. A is just some way of saying like, let's just put a label on the state of technology, and then delta of that state is the risk per unit time that we endure when we're in that state. Does that help? Yeah. This is like the simplest slide. So we should nail this down. It's not. Well, we'll think about that later. Yeah, but for now, A is just sort of a description of the technology state that has no real content to it. It's just indexing features of the world, and we're just saying there is some continuous function from that to the hazard rate per unit time. Yeah, so we're just moving through a path of states. We're not saying anything about them except kind of what hazard rate each one comes with. Yeah.
One thing I never understood in this paper, maybe this version is different, but why this focus on like probability of survival, not up to T, just probability of survival forever?
Because of the thing I talked about at the end of yesterday, where if you're only kind of able to affect the path of like utility in an asymptotically equivalent way, where like the limiting ratio is 1, then if you've got a really low discount rate, if you've got a discount rate of 0, then as big T goes to infinity, like as you imagine, okay, like what if the end of the universe is in like 1 billion years and 1 trillion years?
It's a long term.
Then right. So with the low discount rate hat on, you're only going to care about the probability of survival, basically in the limit. Yeah. So that's, I kind of split up the lecture. Like there's an appendix sort of justifying that way of doing things in the paper, and that's what I stripped out and talked about yesterday, where how like you don't care about relative to X risk, you basically don't care about growth if you're not discounting the future. If the utility benefits of growth are like asymptotically equivalent, so like the ratio of utilities goes to 1 in the limit on any paths that you could actually influence. But this isn't making any normative. Yeah, we're just like conceptually clarifying the relationships between these things, the hazard rate, the probabilities of that. Yeah.
So sigma and
what is sigma? Oh. Nope, not necessarily. Yeah, I mean, so far on this slide. But also, what I'm going to actually introduce on the next slide is that A will be monotonic in time, but that's with no loss of generality, because delta can be an arbitrary function of A. Does that make sense? Okay. So a particular technology path, I'll denote with a little a. So that'll be some technology level at each point in time, like according to some path. So when there's only one path, it's like redundant with big A, but we'll consider different paths and what implications they have for risk. And yeah, as I was saying now, so we'll be considering technology paths that, just to make the math simple, are continuously differentiable, and that derivative is positive. But you see how that's with no loss of generality? Because like the hazard rate's just an arbitrary function of the technology state. Okay, so how much cumulative risk, the big X, the area under the curve, is induced by path little a? Well, it's the integral from time 0 to infinity of the hazard per unit time at that time. But that's the same as integrating across technology states from the one we're at now to the one we're at, like, in the limit on path A of the hazard we endure at each state. And the hazard we endure at state A, at state big A, is risk per unit time at state A times how long we spend at that state. Does that make sense? The total risk you endure in state A, if it's like 1% per year and you're there for 2 years, it's basically 2%. It's not exactly 2% because, like, when it's a positive length of time, you have to, it's like 1 minus 0.9 squared, something. But basically, if you had a 99% chance of making it through the first year, you've got basically a 98% chance of making it through 2 years. Yeah. So another way of putting that is every time you double your speed through a given state, you have your risk of catastrophe in that state. I mean, you might be shooting yourself in the foot because you're just more quickly getting to the next state. The next state could be even more dangerous. But if you spend no time at all in some state, you just hop over it, you're going to endure no risk. Okay. So we can do this change of variables and integrate with respect to technology, where, yeah, A dot sub big A is the rate at which we're moving when we're in state A, or if you like, the rate at which we're moving when we're at the time that we're at in state A. And we'll say an acceleration from path little a to a hat is where you start out with little a, and then a hat, it starts at the same place. It's got the same A0. And then it follows the same path up to some underline A, which could be A0 itself, or it could be later. Then you move more quickly for a while up until A overline. And then you go back to the same old growth rate. So there's some set of states during which you're moving more quickly compared to the original path. That's an acceleration. Now, as people have pointed out, there are other things you might be able to do, like just change the whole direction of technological development. But an acceleration is where you're kind of on the same sequence of states, but you're just moving more quickly along them for some stretch. Okay, that's what an acceleration is. So in this pure state risk model, acceleration is always going to maximize the probability of survival. It'll lower cumulative risk, so it'll raise S infinity. I say it'll maximize it rather than raise it, because it may not raise it. It may be like impossible to raise. If a catastrophe is inevitable, you have no impact, right? You just, a catastrophe is coming eventually, you just get there sooner. Or if you're in a state of perfect safety, there's no catastrophe, you speed up, but you have no impact. But you can lower the chance of a catastrophe by spending less time in risky states. So in this case, the answer is really simple. And you can kind of visualize what's going on here. If on the original path A, this was a hazard rate over time, and then we just move more quickly from underline to overline A, that means that we get to this technology state, overline A, more quickly, and then we grow at the same speed after that. And we just, we cut sort of a vertical slice out of the hazard curve. So we endure less cumulative risk. And this is true, even though to people living around this time, it'll look like acceleration is just kind of making a bad process worse, at least to the safety-focused people living around this time. They might think, oh, we're just making risk even more likely, but there's just no way for that to happen yet in this model. You're just you got to be shrinking the time of perils, or in the pessimistic case, pulling forward an inevitable catastrophe. You're not raising the probability of catastrophe. Note this is a kind of an interesting inversion of the traditional relationship. We tend to think that more concern for the long term motivates like more concern for X risk, and therefore maybe more a desire for slower growth. But here, maybe if you're concerned, if you totally truncate time past here, and you're only concerned for the short term, but you're really concerned with safety, you might think that it's bad to speed up because like you're making things riskier during the only kind of next few generations that you care about. So maybe you want to move slowly if you're short termist, but not if you're long term. Yeah. Aviation? Oh yeah, yeah. So well, I'll get into that later. Here I'm just kind of mapping the space of possibility. I'm not giving you any reason to expect that we're in the left world as opposed to the right world. Right?
No, for sure. I was just like curious about like what you're feeling about these curves, so, like which one is.
Yeah, we'll get there. We'll get there. Yeah. Great. Yeah, I'll call that transition risk, when we kind of, are doing the R&D that moves us from a world without nukes to a world with nukes. The R&D, had some chance of like igniting the atmosphere, and that's about the move from low A to high A. And then the pure state risk is just like the risk per year of having nukes around versus not, or something. Mm-hmm. Okay, so insofar as that's true, we want to assign a different technology index to today versus 1950. A kind of caveat to this is that an acceleration is just you're moving more quickly for some finite stretch of time. Suppose we have like a negative acceleration that lasts forever, so a permanent stagnation. What effect will that have on the probability of survival? That just depends on the state, whether the state we're stagnating in is perfectly safe or not. If it's perfectly safe, probability of survival is 1, right? Because no chance of catastrophe per year, we just stay there. But if the chance of catastrophe is at all positive, then stagnation is deadly for sure, right? So to kind of get to your question, you might wonder if we had a shock sort of returning us to a state more or less like 1925 over and over, would we survive like infinitely many Cold Wars and everything that's happened? And this is sort of a philosophical question because like, well, if we return ourselves exactly to that state, atom for atom, then the answer is yes, because we know that we made it through once. But if what you mean by the state is like, something that's kind of, practically indistinguishable, then I think the answer is less clear. Yeah. Okay. One aside I want to add to the state risk story is, what if you've got what you might call a crude state risk, where the chance of catastrophe per unit time depends arbitrarily on the technology, but then is also like scaled by something that increases over time with the state that you're in. Okay, so there's some hazardous stock M, starts out at some M0, could be 0. And then it accrues over time at a rate which depends on the technology state we're at. Sorry. That's what I meant to do. It accrues at rate little m of AT. So like, in the climate case, M would be accrued emissions, say. And then technology determines our ability to deal with the, a kind of warmed world with more emissions in it or something. In this case, you want to move through the states more quickly for 2 reasons. One, because for the kind of reason that we went through on the previous 2 slides. And the other, because in each state, you're making future states riskier by accruing more of that dangerous M. So that this will end up like qualitatively strengthening the result, unless there are some states in which you can actually, like little m can be negative, and then it becomes ambiguous in those states. Because if you move more quickly, you're kind of like, if you're sucking carbon out of the atmosphere, then in some state, you might want to stay in that state. But anyway, so one application to AI risk comes from sort of a philosophy paper from earlier this year that maybe, you know, a given level of AI technology kind of, if it's advanced enough, it can sort of be destabilizing in some way, and there won't be like a decisive moment that it takes over, but it just, anyway, you can look up that paper, but they have an argument that sort of maps onto the accrued state risk case. Maybe a closer map is to think about an arms race. We'll think actually about arms races tomorrow morning, but at a very high level, suppose your adversary has some chance per unit time spent in a given state of like developing transformative AI and taking over the world and locking in a bad future. The impact of your technology on the chance per unit time that they pull that off might be ambiguous, because, you know, if your A is higher, maybe the risk is higher because like they could steal it, or maybe it's lower because you can use it to stop them. But the longer you spend in any given state, the faster they're kind of increasing their own ability, right? And it could be that like little m is higher when your A is higher because they can kind of, you know, steal more of your tech or something, and, you know, or it could be, you know, the opposite. But m is always increasing over time. That ends up kind of reducing to an accrued state risk model. But we're not going to be working with this because, like, for most purposes, it ends up being qualitatively similar to the simple state risk model, but just more complex. Okay. So that's state risk. So faster is safer if it's all about the state risk. Now, suppose stagnation is safe, but developing new technologies like Russian roulette, to use Jones's analogy, or like drawing a ball from an urn, to use Bostrom's analogy, which doesn't feel as scary. So we're saying the hazard rate per unit time, given that you're at technology state, keep doing this, we're at state A and we're moving at rate A dot, it's 0 if A dot is 0. So, you know, you need to be doing new experiments to be posing any risk at all. And how risky those experiments are depends on the frontier you're at. That's the F of A. And F of A can be basically arbitrary. It can be increasing or decreasing in A. So high F of A means that it just so happens that, like, at the technological frontier defined by A, the next few experiments on like the path that you're on happen to be really risky. Okay. Now, gamma equals 1 would mean that, well, it's all, yeah, I'll interpret gamma on the next slide, actually. But okay, we get the shape of this function, kind of what it's doing. All right. You could equivalently say that like one new technology, like created by one new experiment or something, is a proportional increase to A rather than an absolute increase. And then the thing you want on the right is not A dot, but like A dot over A. And that'll just be a redefinition of F, basically. Does that make sense? Now you have delta equals like tilde F of A times like proportional growth in A to the gamma, where tilde F is just F, your old F, times A to the gamma. But that'll just be another function of A. All right. Interpreting gamma, if gamma is greater than 1, then if you've got a sequence of experiments that you're going to do, they pose more risk if you bunch them all up, do them in parallel, like all in the same year, than if you do them in sequence. Do that, you've got 2 experiments and you do them one after the other. You get 1 unit of risk the first year and then 1 the second year. That's 2. Whereas if you do them in the same year, you get, like, if gamma is 2, you get, you know, 4 units of risk. So you want to spread them out over time. And if gamma is less than 1, it's the reverse. You want to bunch them up. You get square root or whatever of the number of experiments per year. Okay. Okay. For those of you familiar with like Chad Jones's earlier work on this like growth versus risk, he implicitly is using the special case of this function where f of a is 1 over a and gamma equals 1. So the hazard rate is just proportional to a dot over a. Does that make sense? So if you have twice the exponential growth rate, you've got twice the hazard rate. And an interesting thing about that is that that's the case where it doesn't matter how fast you move, right? If you're going to do a certain number of experiments, gamma equals 1 means you're indifferent to bunching them up or spreading them out. Or at least they have the same impact on probability of survival. Okay, so in this case, you kind of maybe get the punchline, but if you're moving more quickly, whether that comes with more or less risk, given that risk is like finite at all and so it's mitigatable at all, depends on gamma. If gamma is greater than 1, then moving more quickly, bunching up the experiments more, is going to raise transition risk. Gamma is less than 1, moving more quickly is going to increase transition. Moving more quickly is going to decrease transition risk. Yeah. So in the Jones cases, it doesn't matter. And this might be surprising because Jones solved for a technology level at which it's like optimal to stop growing because the benefits have just fallen to, and the costs have risen, so that any more technological development, the cost would outweigh the benefit. So he's solving for like an optimal stopping of technological development. Even so, the rate at which you grow to that level at which you want to stop is not going to have any effect on cumulative risk. This is gamma is 1. So it's not about his papers aren't about the speed of growth, they're just about where you want to stop. Okay, Lucy? Yeah, sure. Let's say you only have so much of a budget to like monitor the wastewater for novel pandemics, so you could do a half-hearted job of monitoring the wastewater over 2 years, or you can do it right 1 year. Then maybe you want to do your experiments all in the same year because the public good of monitoring kind of covers more experiments simultaneously. If you think that our ability to cope with the disruption posed by some like advanced AI model that everyone has access to, but we haven't yet like built all the cybersecurity in our government and military and everything to deal with it. Maybe like we'll get like exploited for sure if you have a huge leap in capabilities, but if it comes in slowly, then like we can manage it step by step, and so the risk is really low. Okay. So state risk, you always want to move faster for safety. Transition risk, it's ambiguous, depends on gamma. Let's say we face both types, and we're in the only interesting case where gamma is greater than 1. If gamma is less than or equal to 1, faster is going to be safer. So let's think about the trade-off when gamma is greater than 1. So transition risk makes you want to move slower. State risk makes you want to move fast to risk minimize. All right. So now this is our hazard function. Once again, we can simplify things by asking about risk per technology state rather than risk per unit time. And to minimize, so like, this here will be the overall risk that we endure at state A. It's the state risk per unit time in state A divided by how long we spend there, plus the transition risk per unit time in state A divided by how long we spend there, which is the -1 up there. And just differentiating that with respect to A dot and setting it equal to 0, you find that's the risk minimizing growth rate. Okay. An interesting kind of insight that comes out of this is because, as we've been talking about, the state indexing is arbitrary. Without loss of generality, we can just say that the current risk minimizing growth rate is 1, say, for like the current A. Okay, so if that's right, if A dot star is 1, then what that means is this whole thing is going to be 1. So it's going to be 1 even without the 1 over gamma in the exponent. Right? So this is going to be 1, which means that, h of a is going to be gamma minus 1 times f of a. Now, h of a is state risk. And f of a is not in general transition risk. Transition risk is f of a times a dot to the gamma, right? But a dot, if we're moving at the safest rate, we're just indexing things so that that safest rate is one unit of movement through the a space per unit time. So the optimality condition is going to have a dot to the gamma equaling 1. And so it's going to have the ratio of state risk to transition risk, which will equal f of a, equal to gamma minus 1. Okay, so for example, if gamma is 2, right, if we're in the case where it's like, 2 experiments in 1 year pose like 4 units of risk or something, then if you're wondering, are we moving too fast or too slow, you can say, okay, like, this year is the X risk posed by the fact that we have all these nukes around and all the state risk that we're enduring, is that greater or less than the risk posed just by the new experiments that we're performing this year? Okay. And if those two are equal, I mean, in the gamma equals 2 case, then we're optimizing. And if the transition risk is lower than that, if we're currently year on year kind of enduring more risk from the nukes and from the new experiments, then you want to move faster. And if it's the new experiments that are the main source of risk, you want to move slower. Okay. Yeah, an analogy that's kind of close to my own lived experience is, let's say you're a cyclist by the side of a busy road, and there's some probability per unit time that you get hit, even if you're not moving at all. So that's state risk. But if you bike faster and more recklessly, you might increase your chance per unit time of getting hit. You want to bike just fast enough. You don't want to stop, right? But you also don't want to bike totally recklessly. You want to bike it just fast enough that on the margin, for every like 1% increase in how quickly you go, so like you're getting home safe in 1% less time, your probability of a crash per unit time is going up by 1%. That'll be the case where you're just indifferent between speeding up and slowing down. Yes.
Walking through the rain and trying to think about how fast you walk through the rain. Because walking faster makes you like splash more on yourself.
Okay.
I'm trying to minimize how wet you get.
Sure. Yeah, I guess that would also be an application. No, yeah. Okay. So given that you want to maintain this ratio, the risk minimizing growth rate is going to grow or shrink in line with h over f, right? So like, because you want to maintain them in a constant ratio to each other, gamma minus 1. So for instance, if state risk systematically grows, say, in the technology state at rate alpha, well, alpha can be positive or negative, but if you've got this constant elasticity alpha, and the kind of coefficient on transition risk is, the elasticity in technology is zeta, you can plug that in and you can find that like the risk minimizing growth rate is going to be a to that a minus zeta over gamma. It's just algebra. You can work through it if you're interested. An interesting kind of thing about it is that it shows, yeah, even though there's this risk minimizing growth rate, it can change a lot over time, and in particular, it can fall to 0. So you want to grow ever slower. In the power functional case, the exponential growth rate of a, which doesn't mean anything yet because they're just indexing states. But anyway, it can fall to 0, or it can grow hyperbolically, right? The growth rate can in itself grow and grow and grow. The risk minimizing growth rate. Anyway, and then you can ask how much cumulative risk is posed by that safest path. And again, that's just going to be some algebra, but you'll find that for some exponents, the safest possible path comes with a finite area under the curve, and for some it doesn't. And so, yeah, whether survival is feasible or not will depend on like how the different kinds of risk change over time, kind of on the technology path. Anyway, I'm trying to compress a lot here. All right, we started at, oh, good, okay, we're doing well. Believe it or not, I'm actually a little bit ahead of time, I think. So do we want to go through this at all more? Yeah, Maxine? Can you say more about that? What do you mean by we treat risk as a stock? Delta is like risk per unit time.
Low value. How do you
I mean, like, so the fact that the risk we're talking about is like existential risk to humanity so far has played no role in the analysis. It could have been risk of anything else, like mortality for a cyclist or something. I think, like from actuarial science or any number of fields, finance, we're used to conceptualizing risk as just like the probability per unit time that something happens. So like it, like right now you're enduring some chance per unit time of dying of some heart attack out of the blue or whatever. Well, yeah, it's definitely hard, and I haven't thought too much about like how we would try to estimate. I mean, yeah, even like at a given point in time, people argue a lot about how high X risk is, and you would have to kind of ask that question at like different points throughout history and say, okay, like how fast has X risk been growing, and to what extent has it been due to state risk versus transition risk? So I think ultimately someone kind of trying to make a concrete decision on the basis of a model like this would want to put numbers to these things, and I don't have numbers. I'm just kind of thinking through the qualitative logic.
So a mal-intended person using LLM to create a bioweapon, do you put it in a transition? Because if it's not so fast, then we would have the guardrails and stuff. Is that a nice way to look at it?
It could be, yeah. I mean, so this is a getting into a good question, which is like, if we're thinking about like whether to speed up or slow down, what matters is really just like what features of the world we're able to speed up or slow down. And like if we can't affect how people are using LLMs to like create bioweapons or whatever, then it's totally state risk. Because each year we spend with LLMs of a given quality, there's just like some chance per unit time that they'll be used to create a bioweapon. And then if we like develop the guardrails, well, that's a change to A. The guardrails are a feature of the state, and the chance per unit time of a bioweapon being made and successfully deployed are then lower for higher A right around that A, if like the next thing that we were going to do was create guardrails rather than better LLMs. So in that case, it would just be state risk. But if we can all, if we're thinking about developing a bioweapon and we're thinking about whether to speed up or slow down that, then for us that's transition. Okay. Yeah.
I think it's great. I think at least to me it seems like what is happening here already relies on some functional forms of that. At least to me, like I don't really have a fire on whether I think it makes sense or like different, like how the state of technology interacts with the speed of technology for like
yeah, I mean, so in the very next section, A will start like actually having more of an interpretation. I think what I'm trying to do here is say, let's say you come with some, because remember, like here, like A really just doesn't mean anything. Like A is just indexing technology. So that's why I was I sort of gestured to this before, but it's I totally get that it's a little funny to say like, well, what if H of A equals like H bar A to the alpha? It's like, what does that even mean? But just like for whatever cardinalization technology you happen to like be coming to the problem with, for like wherever you're getting it, how like whatever other interpretations you're using A for, with respect to that way of putting the tick marks on the axes, like that way of cardinalizing A, this is going to be, with respect to that definition of A, the risk minimizing growth rate. And then like how sensible a given functional form is just going to totally depend on like what A means for you. So yeah, it's a bit abstract, but okay. So now maybe I will go on to policy, or no. Now we'll take a break for, yeah, I want to say 15 minutes, but I'm scared it's not. Let's say 10-minute or like 11-minute break to 3:10, and then talk about policy and kind of actually making A mean something. So so suppose the risk relevant features of the world are not just the state of what I'd sort of vacuously been calling technology A, but the state of technology A and of something else you might call policy B. And suppose, to begin with, that the path of that other thing, B, is exogenous to A. Okay, the path of B is exogenous to A, and they both impact risk. Then the risk impact of accelerating A is ambiguous. And hopefully that's kind of obvious, but just to illustrate it, suppose like more advanced tech comes with a riskier world, more advanced policy comes with a safer world, the hazard rate's just A over B, and B is growing exogenously with time at rate GB. Okay, here, of course, stagnating A will be safest, lowering A would be safer still, and you're going to get this qualitative distinction where if A is growing slower than B, then delta is falling exponentially at rate, GA minus GB, negative rate. And if GA equals GB, then the hazard rate's constant. If it's greater, the hazard rate grows. In either case, survival is impossible. So speeding A makes the world safe, makes the world riskier, and it can move us from a world in which we have some chance of getting that S infinity to a world in which we don't. Okay. I've been using the terms tech and policy, but the same logic will apply if there are just like two kinds of tech, say, the kind of risky AI tech and the AI safety tech. Speeding one up in isolation could make the world risky, even though it's all state risk here, not transition risk. Right? So all the logic of before only applies to like if you can really turn up the dial on everything or turn it down on everything. In reality, of course, there's a spectrum, right? Where like some policies will kind of generally speed or slow R&D, like a general increase to like research subsidies or whatever. Or in an automated world, maybe like taxing GPUs or subsidizing GPUs. So to some extent we can target, to some extent we can't. So this is just like the other end of a spectrum where you can only affect one thing, and there's like some other thing which is totally exogenous to it. It doesn't speed up at all when you speed up the thing that you can control. Okay. Given that, like ideally, if you can change not just the speed of motion on a given technology path, but also the direction, then the very safest path will probably not just be a faster or slower version of the path that we're already on. It'll probably be some different path, because there's like a much wider space of possible paths. So you might want to like slow down the risky tech and speed up the safe tech. And that's a great point. Boster made it in 2003. And it's not this paper. This paper is just about speeding or slowing our movement on a given path. But it's probably the more important point, but I think this is like a secondarily important point. Okay, so in this section, we'll be thinking about the risk minimizing technology path when B is not exogenous to A. It responds, and we'll call B policy. And we'll say that there's a planner that is shaping policy to maximize sort of a classic planner utility function, trying to maximize expected discounted utility, given what the technology allows for. Okay. So the planner is being optimal, not with respect to like the long-termist objective or whatever, like just with respect to a normal planner's objective. But they are still being optimal in that sense. And then in the next section, I'll talk about what if a planner is doing something a little closer to just setting B exogenously. And then you're going to have a tension, right? Where faster growth might kind of come with more risk, kind of directly. And anyway, so that'll come in the next section. But for now, the planner is optimal. So what the planner is trying to maximize is discounted expected utility. S, remember, is a probability we make it to time t at all. And I'll say utility is isoelastic with eta greater than 1. Utility of death is just defined to be 0 as usual. As we've seen, that's achieved when C equals 1 here. So that's what a unit of consumption means. And that's why I'm now assuming that the technology state starts out equaling 1 or more, because we're going to be assuming a link on the next slide between technology and consumption. Note that I'm assuming that eta is greater than 1, which is to say that there's an upper bound on utility per unit time. So flow utility. I'm assuming that both because, like, as we've seen currently, when you try to estimate eta, it seems like it's greater than 1, probably. But also to maintain what I think is the more relevant condition when we're thinking about the very long term. I was talking with Avik about this yesterday. I don't know if he's here now. He's not. But yeah, I mean, if you think that, even in the best case, utility can grow at best like cubically, because there's only so much well-being you can squeeze out of a unit of matter or energy, and like we're whatever. Like Holden Karnofsky has some of these calculations where, like, at the rate at which we're using more energy every year industrially on Earth, within I think it's like 7,000 years or something, where we're using, at current rates of growth, we'll be using like all the energy in the galaxy or whatever. So like basically, yeah, I think you probably can't sustain exponential growth in anything we would care about at anything like a cosmic timescale. At best, you get cubic growth if we kind of expand through space. Maybe you just kind of rise to a cap if like we just fill the Earth and we can't go beyond the Earth or the solar system or the galaxy or something. And all those cases will be asymptotic utility equivalence cases, where the long-termist will just be caring about lowering existential risk to a first approximation. And to get that conclusion, you're going to, but like within the world of like normal, like isoelastic utility, you need eta to be greater than 1. Because like, if eta is less than 1, if eta is a half, say, utility is square root of consumption. Well, with like exponential consumption growth, you can get exponential utility growth. And then, speeding up growth now can like have a huge impact in the really long term. Anyway, so eta greater than 1, which you don't even need. I mean, this is very common in papers, just assume eta is greater than 1 anyway. Those Martin and Pindick papers I linked to in the Slack, they both just assume eta is greater than 1. Just focus on the relevant case. Okay. The relationship between technology and consumption is that technology is here going to denote potential consumption. So B is the safety share, the fraction of potential consumption the planner gives up in exchange for safety, either by spending explicitly on safety or just by regulating, like foregoing some consumption because you don't allow some kinds of technology to be deployed. The hazard function is basically an arbitrary function of the technology state and the policy state as indexed by like how stringent it is. We'll say higher safety share means lower risk. We'll say that if somehow we manage to set B equal to 1, like we organized all of society, like literally every moment of every person's day and every machine's day was geared toward making the world as safe as possible, you could get the hazard rate down to 0. Mind you, if you did that, life wouldn't be worth living because like C would be 0 and C has to be 1 to even make life worth living. So it's not going to be like politically feasible or desirable, but we'll just kind of pin down that end of the function with that delta of anything comma 1 equals 0. And to focus on the interesting case, well, interesting and maybe realistic case, we'll suppose that the elasticity of the hazard rate in technology is always less than the elasticity in that fraction of GDP that's not being geared to safety. So what that means is if we double A, we double our productive capacity, but then we have the safety share. So we keep consumption the same, like technology advances, then we use all of that extra capacity for safety. We keep our consumption exactly as it was before. Then we'll say that the hazard rate falls. Okay. Do we get those two assumptions? Well, no. So fixing B, the higher technology can totally mean, I'm not sure how to interpret your question. Alpha being negative would mean that more advanced technology means lower risk. Okay? That would mean like higher alpha, the elasticity is negative, you lower risk. Here I'm saying alpha can be positive. It just can't be higher than beta. So it's got to be the case that more advanced technology makes it feasible to lower risk, but it doesn't necessarily actually lower risk. And we'll see that like in practice, given how the planner optimizes, it could raise or lower risk. Because they can make use of the extra productive capacity to just like consume more, even though that means it comes with more risk. I said like maybe for realism and maybe for interest. If you think that this is not realistic, I think there are cases in which this won't hold. So it's definitely not like, I didn't say like, oh, definitely realistic. I think when you frame it this way, it's, I don't know, it feels like kind of realistic most of the time. But yeah, it could be that like we create some new technology that's so risky that in order to mitigate the risk, we actually have to like cut back on consumption, you know, like on balance. So we're actually consuming less than we were consuming yesterday to deal with this new risk. And that would be a case in which this elasticity was bigger than this one. And if that is true indefinitely, and if the risk we're starting out at is positive, then there's no way to eliminate risk at all, because we can just stagnate and then we get, you know, if we have a positive hazard rate, then we die, or we can grow. But the only way to mitigate risk in that case, where the inequality is reversed, would be to like lower our consumption ever more over time. Like every time we double our productive capacity, we cut what fraction of that we turn into consumption. We cut the 1 minus B by more than half. And then eventually we hit an existential catastrophe by other means. We just kind of make life not worth living because C is going to be below 1. So that's like, that's totally a logical possibility. Again, I think that's probably not how it works most of the time. But if it is, that's also interesting, I guess. But it's not much math to do. You just say, okay, we're doomed like regardless. So we'll think about the case where it's actually up in the air, and what the policymaker does can have a difference. So for example, this would be the case in which alpha and beta are constant. You just have like constant elasticity, okay? And then the alpha, supposing that alpha is greater than or equal to 0, that's just adding the assumption that in the absence of ever more stringent policy, the probability of long-term survival is 0. Because like technological advancement isn't going to make the world safe on its own. So we're kind of in the right graph as opposed to the left back when we were thinking about state risk only. You know, like absent policy, more advanced technology comes with more risk. And again, it's just going to be kind of simple and obvious that faster is safer if alpha is negative, right? But now we're going to find that faster can be safer even if alpha is positive. All right. So given tech path little a, policy path B sub A is going to be the optimal path for the planner. Turns out that it exists and is unique. S, X, and delta can be written as functions of the technology path and the policy path. V will be the expected value of the future to the planner as of t, assuming that we've made it to t to begin with. Obviously, if we haven't, then it's 0 or whatever. The planner doesn't exist, but yeah. So it's the integral from t to infinity of the subsequent discounted utility, probability that we make it to tau, given that we made it to t to begin with, times utility and consumption as of tau, which is just going to be, a tau times 1 minus b tau, right? And then because we'll be assuming that the planner is optimal in this section, we can just write S of A or V of A or whatever, meaning S of A comma B sub A. Okay, so technology path A will induce the survival curve implied by that technology path and like the planner's optimal policy path given that technology path. Okay. We get the notation? All right. And the we'll let B tilde be like the consumption share. So this is 1 minus the safety share. Yeah, 3 things to observe before moving forward are first that the value of the future is positive. This is, you can just see this from the fact that if we just don't spend anything on safety at all, well, that's feasible. And that'll induce a path of flow utility over time that is positive at first, because or at least it's not negative at first, and it grows. We know it's not negative at first because we assumed, remember, that that A0 started out greater than or equal to 1. So like it's feasible, if you don't spend anything on safety, it's feasible to create enough consumption that life's worth living, hopefully not at the super strong assumption, and that it rises. So, at worst, in any future year, we're getting 0 if we're dead then. We're getting a positive amount if we're not. So that's feasible. That's always going to be feasible at any time going forward. So the value of the future is always positive. Second, faster future growth, I'll use the word growth to mean technology growth rather than consumption growth, makes the future more valuable. So if we're thinking about some alternative path A hat, such that it's like strictly higher than the baseline path A at all future times, then the value of the future is also going to be higher today. And the intuition there, it's kind of just, I guess, similar to what we just went through. Higher A's, given that D2 assumption, higher A's make it at least feasible to just cut back on, they increase our productive capacity. We can cut back on our actual consumption so that we have the same path of consumption over time as we had on the original path A before we shifted to A hat. But we're safer at every point in time because we're using all of our additional capacity for safety purposes. And because the value of the future is always positive, safer is more desirable. And then finally, the value of the future rises over time, but to some finite limit. We know that it's increasing because, like once you're at a later time, the subsequent technology path is like higher at every time than it was earlier in time. Do you see what I'm saying? Like once you've reached a higher A, then going forward, the whole path is going to be like higher at any point in time than it was for like, every step forward from the earlier time when A was lower. And so we know it's going to be rising, and we know it can't rise forever because at most, flow utility is what it is when C is infinity, which is 1 over eta minus 1. Yeah, like C to the 1 minus eta minus 1. The first thing goes to 0 as C goes to infinity, and then you get minus 1 over 1 minus eta. So yeah, utility's got an upper bound. And so the value of the future has an upper bound that's just like, what if you got that maximal flow utility forever? You're discounting at rate rho. So that's the maximal value of the future. Okay. All right. We all good on the 3 observations? They're all pretty intuitive, I think. So. Okay. So the planar optimal policy will be characterized by this first order condition. The loss in flow utility from increasing safety spending a little bit, or in proportional terms, increasing the safety share B a little bit at any point in time, in general should equal the benefit of increasing spending by lowering the hazard rate at that time, and so increasing the probability that you get the whole subsequent value of the future VT as of that time. So it'll equal the two if you're in an interior solution where you're actually kind of making the safety share positive. But it could be greater if the optimal safety share is actually 0, if you're in that corner solution, right? Then you might want to actually increase the probability of a catastrophe even more than than the current rate you're enduring, if you could turn that into more consumption, but you just can't. So you don't even want the first unit of spending, but at least the loss has to weakly exceed the benefit. Yeah, that's the gain. Sorry, that's the loss in flow utility. So this will be negative, right? Higher B means lower consumption, means lower flow utility. So this negative term has to be less than or equal to this term, if we just move this to the other side of the inequality, which is the benefit that comes from lowering the hazard rate by raising safety spending multiplied by the value of the future. And yeah, you're never going to want to set a safety share of 1 because then life's kind of not worth living. And you can see that also just from the lower anotic condition on U, right? The first unit of consumption is infinitely tasty. All right. So just kind of working through, just for intuition, working through the constant elasticity example. Let's suppose that the technology path is just exponential at rate G. What does that imply? Well, the marginal utility, this thing, of raising B is going to be, so you've got, yeah. It's going to be a to the 1 minus eta b tilde to 1 minus b to the negative eta. That's sort of asking the question, you're going to get a negative if we're differentiating with respect to b, then we're going to negate it. So like the benefit of consuming more has to be less than or equal to the cost via raising the chance of catastrophe. And now we're just differentiating our constant elasticity hazard rate. So we're pulling the beta down from the exponent there in the hazard rate. Because we're working with this. Wait, where was the example? Yeah, we're working with this hazard rate, and like b tilde is 1 minus b. And then, yeah, rearranging it, you find that basically the optimal consumption share is just the minimum of these two terms. You just sort of rearrange it, you solve for b tilde. And so you're not going to want to spend anything on safety. You're going to want to have a consumption share of 1 up till the point that like the risk has gotten high enough and the marginal utility of consumption has gotten low enough that you want to start spending on safety. And then as A rises, you're going to want to spend ever more on safety. So b tilde is going to fall. But V is going to be rising, and that's also going to make you want to spend more on safety, but that's only going to rise toward that upper bound of V bar. So this whole thing will be a constant asymptotically, and B tilde will fall as A grows with elasticity given by that exponent there. So early in time, the consumption share is 1, and the hazard rate is going to grow because we're focusing on the interesting case where more advanced technology comes with more risk. But later in time, the trend's going to reverse. So the hazard rate's going to grow at a negative rate because it's going to be growing directly because of the A, the alpha. Then it's going to be falling because of the B falling, and the B is going to be falling as the A rises. And on balance, for any pair of constant elasticities, it turns out that the second effect outweighs the first. The increases in the safety share outweigh the direct kind of risk imposed by more advanced technology. And so you end up getting a hazard rate that, in this constant elasticity example with exponential growth, falls to 0 exponentially, and so you've got a positive probability of survival. This is what it'll look like. The safety share rises over time, and the hazard rate rises early in time while we're not spending anything on safety. Then we round the curve, and we are spending on safety, and we're making the world safer. This funny kink is due to the fact that there's the way the hazard function is written, there's no lower Inada condition on safety. There's not like infinite benefits to the first penny, infinite benefits per dollar to the first penny that you spend on safety. So you don't want to spend anything for a while and then suddenly want to start spending. But if you just kind of add a wrinkle to the functions that you do have a lower Inada condition, you're always spending a positive amount on safety that just rises gradually. And the function the function of the hazard rate over time maybe looks a little more reasonable. Okay, but we get the kind of qualitative dynamic. It is very similar to a lot of work by Chad Jones on how over time we want to spend more on kind of safety and kind of the medical context or in just workplace safety or whatever. But also and more directly relevant to Nancy Stokey's environmental Kuznets curve, kind of observing and theorizing about the observation that for a lot of bad things you could put on the vertical axis, like pollution, or like smog in cities. When we're poor, we're willing to not spend on cleaning up that mess because like the marginal utility of consumption is really high. And the loss of life or just the nuisance of having a lot of smog we care relatively less about. But then when we're richer, we have more to lose, marginal utility of consumption is lower, then we invest in cleaning up the mess. And so when you plot smog over time, and it's a totally undeveloped country, it's really low, and then it gets high, and then it falls again. So it's just the exact same math, the same shape of the utility function, same logic. I just went through that example with constant elasticities. There's a much more general result in the paper showing that under, I think, pretty wide conditions, obviously you can make up your mind about that, but under some much broader set of conditions than the constant elasticities, this can make the cumulative risk finite as a result of the optimal policy response, when rising or stagnant technology alone would make survival impossible. So like policy can come to the rescue a fair fraction, under a pretty wide array of conditions about preferences and technology. That's kind of the first point. You get this existential risk Kuznets curve, if you like. And the second takeaway is that the policy response strengthens the faster is safer tendency that we saw in the state risk only case at the beginning. What do I mean by that? So if policy at a given time had depended only on the state of technology at that time, then we would have like the optimal policy path would at T choose a level of safety spending that just depended on the technology state at T. So we could just write B of AT. Okay? In that case, the hazard rate would depend on the technology state at T and on the technology state at T again, just via how it instantaneously shaped policy, right? That would just reduce to a function of technology, just like in the state risk only case. And so everything we were concluding before would just hold through trivially. right? If you're just moving more quickly through on the technology path, you're also like moving more quickly on the policy path, because like at any given technology state, the policy would just be a function of the technology state. So it's basically just one state variable. But this is not what's going on here. Here, more advanced technology motivates safer policy on the whole, but also the prospect of faster growth from a given time forward motivates safer policy, because the value of the future is higher from like forward-looking. The forward-looking planner at T is like willing to spend more to save a world that's more valuable, and a faster growing world they see as more valuable. So this is just a theoretical point, but it does kind of map onto something I hear often from like people at GovAI, that, like, I don't know, I was talking with Marcus Anderyoung, and he seems pretty convinced that in Britain and throughout Europe, one thing that makes them really hesitant to regulate AI too much is that, they feel they haven't been growing too much, and they don't, they want every % of GDP they can get, and that strong growth prospects, whenever those are looking more promising, they're like way more keen on sacrificing some of that for anything really, but including regulating AI. So just to kind of illustrate the two parts of this result, the first is that we're strengthening the tendency for acceleration to lower risk via making the first scenario more likely than the second. So if we're just more likely to be in this like sort of time of peril scenario than the scenario where doom is inevitable, then we're more likely to be in the scenario where you can have any impact whatsoever, because here you just have no impact at all. But then secondly, even given that you're in the scenario, speeding growth lowers risk by more than it did in the pure state risk scenario, because while the acceleration's underway, at any point in time, subsequent growth is going to be faster. Does that make sense? Okay. Finally, something that I think is kind of interesting about this this model is something I glossed over yesterday, but just when I was like introducing the kind of argument for long-termism, or the argument for kind of thinking that astronomical value is at stake if we kind of raise or mitigate existential risk today. Something that David Thorstad in particular has really emphasized, and people have observed for a while, is that even if you think X risk is really high today, and that it's really feasible to mitigate it, as if that phi is really high or whatever in Chad's model, even if you believe all of that, there isn't like astronomical value in lowering X risk unless you think that X risk will eventually be low. If you think that it's high now, we can save the world today. But then, like, Mr. Incredible at the beginning of The Incredible, it's like, no matter how many times you save the world, it always gets back in jeopardy again. Then the future is going to end soon anyway. So like, yeah, you want to spend a lot to lower X risk for Chad's reasons, because the value of statistical life is really high, and this generation cares a lot about itself. But you don't get the astronomical value, because the future is not going to be very long. You need the assumption that risk is high now, we can lower it a lot now, and risk will be low in the future. So once we save the world once, it stays saved. And in that sense, this is like maybe kind of an important point, because like this is a real open question. Will the world stay safe, right? And I think, I don't know, it's just sort of a theoretical argument, obviously, but if X risk looks anything like smog or various diseases or whatever, then that people are willing to move into cities and urbanize and that die at a higher rate due to disease, and then they clean up the disease. And you see this pattern a lot, and it kind of, I think we understand the theoretical basis for it. In principle, it should apply to X risk. Gives me some hope. Okay, any questions on that before I move on to like what if policy is not so optimal? Yeah. Well, we see this pattern where there's some bad thing that comes with technological development, at least if you don't like put additional effort into mitigating the bad thing, like smog or like urban diseases. And you look over time at how much we've suffered from that as like technology has improved in a given like region. And you see it goes up and then it comes down. And then you look into why it went down. It seems like it's because they got rich and started caring more on the margin about fixing the problem than about getting richer still. So they're willing to pay taxes or like regulate their factories or whatever.
It seems to me that this is in like a hopeful insight of like semi-endogenous growth. It was like, oh, then stop growing the population at that point. And it was like, stop using the technology. And then there will be astronomical values for the future.
Well, it depends where we stop the technology, right? If we stop at some rate that still comes with, 1 in 10,000 per year chance of blowing ourselves up or whatever, that's still not that astronomical of a future. So you want to get so much technology that you really batten things down. We're really good at making things safe, so it can last a long time. But I'm not quite sure I see the connect. So you're saying semi-endogenous growth theory is optimistic because if we don't automate R&D, if people stay necessary, and if we stop having people, the optimistic point is that we have no people, we have very few people, and we have very little technology for a long time. But at least we'll have a long future because, yeah. Again, I don't think I agree with that conclusion, both because on anything like current margins, I think the conclusion would be you want more technology in the long run. We don't want to just stick with our current technology. Maybe you disagree. Anyway, that would be what I would think. But then secondly, we were talking about it's like the whole reason why I assumed that upper bound on utility was because in order for it to be the case that, like, from a long-termist perspective, basically all that matters is lowering X risk, it's got to be the case that all of the utility paths on offer are like asymptotically equivalent in the sense that the ratio between them goes to 1 as we go to infinity. If we could have way more people and we're just not having them, right, then it stops being so clear that the best thing is to lower X risk. Maybe you want to double the population, even if that comes with a 50% chance higher, a higher chance of risk per year or something. So if you just cared about the length and not at all about the size of the population, then it could be optimistic. Okay, and then finally, what if there are policy frictions? So, I don't know, lots of ways you could try modeling this, but one that I think is sort of tractable and captures a fair bit of what people could worry about. Let's say the way it works is when tech is moving fast, each unit of like actual safety spending, actual B, comes with less effective B. You have to spend a certain amount, but as far as the hazard function is concerned, it's as if you spent less because the dollars are not spent, or like a smaller fraction of them are spent in a way that's targeted to the actual threats of the moment. Because like the laws were passed last year and like the states changed or something. This will function like transition risk. And indeed, we might think of this as micro-founding transition risk in at least some cases. When the world's moving fast, there's more risk because policy is going to be more mismatched to the actual risks that we face. So again, there's lots of like potential functional forms for this you could think up. Here are two that turn out to just be especially tractable. Let's say effective safety spending is actual safety spending, this is the share, so it'll be between 0 and 1, okay? And we'll raise it to a power that's greater than 1 and increasing in the rate of technological development. So it'll fall because you're raising something less than 1 to a higher power. And again, we're going to have that M thing just kind of be arbitrary, but this is increasing in A dot. So faster growth means less effective spending per actual spending. Or we could just say we divide B by something that looks like that. This is hopefully pretty flexible. I'm not saying anything about what form M takes or what gamma is. This will play really well with a hazard function that takes this form. Where what we're saying here is, if like here we have our nice lower Inada condition on safety. So like, we're saying if you don't spend anything, then you die for sure, like instantaneously. But it's like negative log of B. So this is the hazard rate. But then it can be like rescaled arbitrarily depending on the technological frontier at any given time. That's the H of A. We're going to need the elasticity of H and A to be bounded below 1 in order for it to be possible to mitigate risk enough to make the probability of survival positive. Okay. So then if you just like plug these into 11, then you just recover the like state risk only. Sorry, no, you recover the transition risk plus state risk models that we went through before. So you kind of basically all the conclusions we had before about an optimal growth rate that's as long as gamma is greater than 1 will go through. And then like which functional form we chose up here will just depend on whether safety spending ends up lowering state risk alone or lowers both kinds of risk. Yeah, so you can see that like fixing B, we like exactly reduce to the old hazard function. So yeah, so you get that finite but positive risk minimizing growth rate. From that baseline, there is a tendency for the insight of the previous section to hold. So faster growth will tend to raise the value of the future, which will tend to motivate more safety spending. And so that'll be a shift from the transition plus state risk model from before. We found our A star, like our risk minimizing growth path. And now the risk minimizing growth path will be a little bit faster because you get the effect that we were talking about before, where faster growth motivates it's not going to be as effective as before, but directionally, if faster growth means the future is more valuable, and so the planner spends more, then the risk minimizing technology path will be a little bit faster than what we solved for before. But actually, even this point turns out to be technically ambiguous because it can be the case that speeding up so extremely lowers the effectiveness of spending that the planner is like, okay, I'm not even going to bother trying to spend. Anyway, and that can also like lower the value of the future. And then, so for extreme enough parameter values, the sign of this tendency can be reversed. But you would need like this, you'd end up with weird implications like R&D being bad on balance from the planner's perspective. Anyway, just to kind of visualize the cases. Well, any questions on that first? Like policy friction in general? All right. So just to recap, in the state risk only world, without policy, then if we're in the hump sort of scenario where higher, I shouldn't even say higher values of technology, but like levels of technology that we just are on path to be in the future will come with lower hazard rates. And they'll do so fast enough that the area under the hump is finite, that right tail, it falls to 0 like faster than 1/t. So the integral is finite. then the risk minimizing growth rate is just infinite, right? You want to move as fast as possible. If it doesn't fall to zero fast enough on its own, then the risk minimizing growth rate is anything, because risk is 100% no matter what. Policy, as we've seen, kind of expands the range of cases in which you can have an impact. And it also maybe expands the impact that you have by speeding technological development. But it still leaves some room for cases in which the smog stays up there forever, and we die for sure, in which case the speed of growth isn't gonna make any difference to the probability of long-term survival. And then when we think about transition risk on its own means you want to move really fast if that gamma is like less than 1. So you want to bunch up the experiments rather than spreading them out. You want to move really slow. So the slower, the safer. If bunching up the experiments comes with more risk than spreading them out. And in this edge case in the middle, that like is the implicit assumption of Chad Jones's earlier papers on this, then it doesn't matter whether the experiments are spread out in time or bunched up. And so the risk minimizing, any growth rate is equally risk minimizing. And then, yeah, when you build in the transition risk, there's going to be some, you want to move really fast unless gamma is greater than 1, in which case there's some finite risk minimizing growth rate, which could itself change over time, but it'll be finite at any given point in time. And we just went through the frictions just now. So yeah. The very last thing I want to say about this, or any questions about the recap? The very last thing I want to say about this is that this new good stuff I keep harping on about can overturn all of the policy stuff. So it's not going to overturn the state risk point, obviously, right? Like shrinking the, the area under the curve has got a lower risk. But yeah, as we actually just went through this morning in correcting an error I think it was answering one of your questions, Jack, about the VSL, like when can the VSL fall? Yeah, it can totally be the case in principle, even though the standard ways of modeling utility functions don't allow for it. It can be the case that we come up with new technology that makes life more valuable, but it really, really raises the margin utility in consumption. And so we're sacrificing more utility by spending on like safety rather than consumption than before, right? Like if you invent heroin or something, like, it might be the case that, safety for a particular person falls, like they're willing to accept a higher hazard rate because like the margin utility of consumption's like gone up by so much that even though you might think, well, but they've got more to lose because now their life is so good because they're on heroin. So maybe they want to like be extra safe. Like, no, like you don't want to be selling them health insurance. Like their hazard rate has risen. So if we invent goods that like really raise our margin utility and consumption, then that can like lower the tendency of a planner to tax citizens, taking away some of their consumption to help save their lives. And, historically, again, with all these examples of Kuznets curves, we don't see this. We see that like safety comes with wealth on the whole. But if we're imagining that AI doesn't just kind of speed up technological development in a totally like neutral way that extrapolates from the past, but also like maybe changes the direction, makes it easier to develop kind of new goods or something, relative to like creating lots of quantities of the same old goods in a way that very much lowers the marginal utility of consumption without raising the utility level that much. Then it could be something like this is more of a worry. But I'll just note at least that it's a logical possibility. Okay. All right. Actually kind of on time for once.